Hi, welcome to another BlackHat. I'm Dan Kaminsky. This is my 6th BlackHat. That is not the impressive part. The impressive part is that it's my grandmother's 3rd BlackHat. My grandma is more elite. Wrote a couple books, used to be part of Cisco, used to be part of Avaya. I'm presently partnered with a company called IO Active. They're a really interesting consulting firm up in the Seattle area. That's not good. One of the blue hat hackers, so I've been looking at Vista for the last 10 months. The amount of it I can tell you about it, nothing. However, there's this huge track tomorrow that's going to talk about some of that stuff. We don't have much time, so we're just going to blast through stuff, and unfortunately some of the live demos are going to have to be cut. But what are we here to do today? You may or may not notice, I never tell people what I'm going to be doing in advance because, well, I don't always know what's going to work. But what we're going to do today is we're going to discuss tools for enforcing network neutrality. We're going to discuss the results of scanning 2.4 million SSL servers. We're going to fix online banking. Okay, not entirely, but a little. We're going to fix a security hole that I put in OpenSSH during my first BlackHat talk. We're going to make entropy recognizable. Now, this is the useful thing for crypto systems like OpenSSH. This is really useful for fuzzing. And for those who are paying attention in the security world, fuzzing's gotten a lot more relevant. And of course, it being me, pretty pictures. New for this year, useful pretty pictures. Even if they're at 100 megapixel. Don't believe me? At the end of this talk, we're talking about visual bin diff. But for now, enforcing network neutrality. First section here. Well, telcos have effectively stated that they wish to spy upon and selectively censor traffic, so as to maximize revenue from those who will pay the most to see their traffic pass unhindered. This is, oddly enough, a familiar problem for us. Alice and Bob are in prison and are attempting to communicate without the warden interfering. This is the kind of stuff that you think about when you're starting to learn security, you go to the academic instructions. Somehow, academic instruction became my ISP. I just work here. Now, you may or may not believe the premise, but hey, just quoting Comcast here, to accommodate the needs of our customers who do choose to operate VPN, Comcast offers the Comcast at Home professional product. This product will cost $95 a month. Will afford you with standards that differ from the standard residential product. You guys didn't think this whole network neutrality thing had anything to do with video, right? Do you understand how much money that YouTube loses every month? You've got a friend or a kid who works for minimum wage, your kid's making more money than YouTube. It's actually about $1,100 a year per telecommuter. Granted this is a tech talk, but can't ignore the geopolitics. Oil prices have tripled. We're probably going to see a significant uptake in the amount of telecommuters. Get a lot more telecommuters, get them paying $100 a month, you're making $45 billion a year. It has nothing to do with video. So now, the assumption on my part is that pretty soon, most companies are going to realize it's a grab for their pocketbook. And the debate about network neutrality is going to leave, should the network be neutral, and become, is it possible to detect non-neutral networks? And the answer to that question is yeah. TCP bandwidth estimation, an elegant weapon for a more civilized age. TCP automatically determines the amount of available bandwidth between any 2 points. If you have 2 nodes that are using the same network, they do not actually directly send packets to each other. Rather, they detect interference caused by the behavior of the other nodes. Use that interference to tune the particular speed at which they'll communicate. Now, in this model, in this environment, very elegant, I must add, dropped packets are a source of information about the other traffic going on the network. TCP is using interference. If we can control the interference, we can actually learn about what the network is defining as interference. So check this out. Active network programming. Yeah, I think I'm just going to be talking about TTLs for every single talk I ever do at BlackHat. One of the things you can do when you send traffic on a network is you can specify how many hops your traffic is going to go. You do this by changing a value in each of your packets called the TTL, the time to live. Now, TCP, what it discovers is, I'm going to send traffic at 5 kilobytes a second. If I exceed 5 kilobytes a second, packets start dropping. So what do? We exceed 5 kilobytes a second for 1 hop. Nothing happens. 2 hops. Nothing happens. 3 hops. Nothing happens. 5 hops. Oh, now packets start dropping. Oh, now I've determined that the bottleneck on my particular session is 5 hops away. This is actually a generically useful thing you can do. And you don't need to use any custom tools that I've written, although I am writing them. You can just use HPing. HPing gives you everything you need to go ahead and inject some traffic on top of a fully loaded link and have it go 1 hop, 2 hops, 3 hops, etc. Why is this about network neutrality? Because we can control the contents of those extra packets. Not just send extra traffic, we can send extra traffic from Viacom, extra traffic from NBC, extra traffic from Procter & Gamble. The idea is that we can actually modify what we're proposing as interference, and we can see, does it or does it not cause packets to drop? Now you might say, but Dan, what if they're using a filter that requires fully established TCP sessions in order to control whether a preferred service is allowed? Well, it's kind of cute, you know, Google, a bunch of other companies actually have code that lives on the client. And if you have code that lives on the client and code that lives on the server, you can have the server pretend to be Viacom. You can have the client pretend to be responding to Viacom. And so as far as the network in the middle sees, oh, there's a full great session going on between you and Viacom. You know, packets come in, ACKs go back, it's all great. Network has no idea there's anything in the middle. You can also do content preference. You can have it say, we're going to send some encrypted traffic over this link. Let's see if encrypted traffic is marked as specially interfering. You might say, encrypted traffic? Why would they interfere with encrypted traffic? I thought this was about video. Well, let's look at the history. Well, first of all, they did, right? I mean, that was the whole point about blocking VPN traffic. This is why Washington State had to go ahead and take a huge number of people off of Comcast and put them on some other network because Comcast was blocking the state VPN system. So A, well, they did it. That's always good in a court of law. B, let's look at the international precedent of any time you put people behind a restricted network, they try to find a way to hop their way out. And when they try to find a way to hop their way out, often one of the best things to do is to apply encryption. The problem is, from the new model being proposed, and this is theft of service. You might have some malicious, you might have some content that could be charged extra for inside those encrypted packets. Now, let's look at what encryption is actually used for legitimately. A, I mean, we're talking legitimately from their perspective. A, workplaces that make money from their employees at home. And B, e-commerce sites that make money from consumers at home. In both scenarios, you have money being involved. And with money being involved, you have an increased ability to pay. So one could completely legitimately imagine a future where if you want to route encrypted traffic over the publicly available common carriers, you have to pay extra. That's something as a security professional that terrifies me. It is enough of a pain in the ass to get people to adopt secure solutions without, I wonder if the telco is going to filter my traffic. So we got to do something about this. And while I can't do much on the legal side, but can I give you guys a test, a mechanism to discover if this kind of filtering is in place? Yeah, I can do that. So, moving on to more technical subjects, SSL. SSL is a fun system. Has a couple of rules. First of all, do not put things you would not want to be public in a public key. There's a reason they're called a public key. You would think this was obvious. Do not put the same key on multiple boxes. SSL does not have perfect forward secrecy. If two boxes have the same key, they can read each other's traffic. No one would ever ship 2 devices with the same key. These are the things you find when you hit every IP address in the world. There's some weird stuff out there. I don't exactly know what's going on in terms of sending traffic out there. All I can say is that I've actually removed some details from this talk because I'm just not as confident about them as I'd want to be. But again, if you are the sort of site that does not want people knowing all your internal DNS names, be very careful what SSL certs you let the public scan for, because SSL certs actually assert a name of a host. For example, if you have a honeypot whose purpose is to trick hackers into attacking it, you might not want to call the box honeypot.yourcompany.com. And if you do this, you might not want to have it be front and center on the SSL cert. So, what did I see when I scanned all these boxes? Good news. 90% of keys were only on one box. 9 out of 10. Awesome. Bad. 10% of keys were repeated. A lot. Like, so much that 1 out of 3 SSL servers had a repeated key. 10% of keys caused 2 out of 3 SSL servers to be in a defined insecure scenario. I'm not going to name names, but there are a depressing number of VPN concentrators and embedded devices that have fixed SSL keys. They burn one in at the office. They think, oh, well, you know, it's not like we're getting it signed, so what's the problem? People have to randomly trust keys anyway. Well, the problem is I just sniff some traffic for you managing a particular VPN concentrator, and I just hand that off to SSL dump with the key that I have on, you know, the one that I bought off the shelf, and now I'm decrypting all your management traffic. Really depressing reality, and again, not naming names. There is a site that really should know better, who probably has people in this room, who probably knows I'm talking about them right now, that appears to have, 60,000 machines, servers with the same SSL key. Wow, that's awful. You really should know better. Caveat, the absolute numbers are pretty sketchy. There's boxes that have keys that move around. I don't know what's going on. Someone in this room might know more. But in the meantime, there's a much more obvious SSL flaw that we can go ahead and address. And that involves the world's most depressing Google search. If you search for why is this secure, you will see site after site that has a login page that says, please put your credentials in here. Now this one's great. Social security number or tax ID. Why is this secure? Well, it sure ain't secure because that's SSL, because that form's not coming in over SSL. I'm not joking when it's like my grandma, who granted has been at 3 BlackHats, can hack 26% of the top 50 banks in the country. Dear God. It's called you change HTTPS to HTTP. There's no authentication on it being an S, and so one character and you win. Just saying, maybe we wouldn't have as bad of a problem with phishing if we weren't training users to trust a little icon on a web page. Look at this. This is great. 26% of the top 50 banks, they all put in this little lock. I did not know there was this much clip art for locks, but it's impressive. So how did we get this problem? Why are all these banks putting these forms on that we know are insecure? They know. I mean, I'd love to take credit for discovering this, but come on, people have been whining about this for like 2 years. I've got a reason for actually bringing it up now. It's called a solution. But the choice is here. Either A, you force everyone coming to the bank's website to use SSL. This doesn't fly because guess what? Deploying large-scale SSL solutions doesn't really work. 2, you could force everyone at the homepage to click through to a login page. Now, I used to, believe it or not, be part of Linux's GNOME project. I used to be a UI guy way back in the day. And let me tell you, when you put a username and password form in front of someone on every single page they go to, they think, wow, I should log into that. It's like in literature, Chekhov's gun. Wow, I should really be using that thing. And banks love it when people use online banking. Because guys, you're all a pain in the ass to deal with, and they'd much rather you just go to their computers and you do the work. Wouldn't that be great? Then you just like store their money, and it's wonderful. So every single time this subject that comes up, they're like, well, you know what? If we fix that, we're going to reduce the usage levels of online banking, and that will cost us money. So they don't want to do anything. And, that's a position. Reasonable or unreasonable, it's a position, business decision. And so what you get is allow people to log in directly through the homepage. Question, is it possible for users on online applications to use a homepage login screen securely? And the answer is yes. Fourth option. So web pages are not static documents. They're not sheets of paper. They can recode themselves dynamically to user input. Now, on HTML, you have a function called iframe. Iframe is a mechanism for putting a mini window of a web browser into another page. Iframes do not need to be visible. They can be 1 pixel by 1 pixel. It's somewhat well known that you can iframe to another page and then get that other page into the browser cache. So when you go over to it, it just pops up instantly. Great. What's not well known is that you can actually have a secure link, an HTTPS link inside of the invisible iframe, and it'll work. It'll negotiate the crypto, it'll cache the contents. Why? Because as long as you're still on HTTP, you're not making any assertions about the security level of the iframe. You're just retrieving content. Browsers allow you to upgrade securely a lot easier than they allow you to downgrade it. And that is a good choice. So the solution is this. When you log into a website, you need to put in your username, right? While you're typing in the username, that's when you go ahead and spawn this iframe, populate it with the HTTPS, preload all the contents, and then when they hit the secure site, then they hit the password, when they hit the stuff that they shouldn't be putting in publicly, bam, you move them over. It's great. I'd give you a demo, but there isn't time. The code is really straightforward, though. We have a username field that runs the pre-cache function. We have a password field that, as soon as it's focused, switches the page over. And we have a span called the text ID. Excellent. Looks like we're actually getting a video for the other side. This pre-caching, what it does is a singleton. It'll only run once. You only want to be launching that iframe once. You don't want to fill the page with it. But all it does, it goes to the text display, the little span, and it throws in an iframe. What does this end up looking like? Well, you do a username password field. As soon as you type in ABCD, bam, you go ahead and that iframe opens up. As soon as you go to password, you redirect over. Great. Now can we stop abusing SSL? Woo. As long as we're talking about bugs in crypto systems, I'm kind of sort of responsible for one. I mean, not really, but kind of. So was anyone actually at my SSH talk 6 years ago? Holy crap, that's awesome. Seriously, I'm surprised I was there. No, So one of the things I found, SSH being a crypto system that allows you to connect to random hosts on the net, not random, but your host, do it securely. I found instead of just getting a shell, instead of just getting a text link, you could actually move arbitrary web traffic, IM, all this kind of good stuff. You can basically get like a poor man's VPN link. Now the problem is when you do this with SSH, it was actually leaking DNS locally. DNS being a subject that I took up a few years later. Now what I ended up doing at the time, a couple years back, is I got the OpenSSH guys to add support, not for SOCKS 4, which doesn't support doing remote DNS, saying I'm not going to give you an IP address, here's a name, you look it up. I said support SOCKS 5, which allows you to put in a name. And the OpenSSH guys did that, and through an undocumented option, Mozilla supports it. But not all clients IE7 support this. So is it possible to fix things like IE7 without going through the code? And the answer is yes. Why can't we forward DNS over SSH directly? Well, you see, DNS is a UDP-based protocol, just individual messages that fly back and forth. Now, we could put a huge translation layer in where it receives UDP packets and it runs NS lookup commands, and it's this big, ugly mess. We could do that, and then Theodore Rad would look at the code patch that I'm suggesting for OpenSSH and be like, I'm going to shoot you. Or, it turns out DNS will run over TCP. You just have to tell it won't work over UDP. So you put up a silly little server that all it has is just, oh, you're coming to me over UDP? No, that isn't going to work. Truncation bit equals 1. And the thing goes, oh, well, let me retry that over TCP. And that SSH can move just fine. This is a nice general purpose strategy for anything that's trying to use socks in an environment where the client doesn't necessarily support it. Works well. Sadly, I'm totally going to hell because, I got DNS over SSH here, and later I got SSH over DNS, which means DNS over SSH over DNS means, yes, I finally did implement DNS over DNS. Malkovich. Okay, I eventually have pretty pictures coming. So, wetware bugs. SSH has another problem. The authenticity of law 1.2.3.4 can't be established. RSA key fingerprint is 09A9B199841777D, etc. blah blah blah. Am I supposed to do something with this value? Okay, seriously, crypto designers look you straight in the face and go, yes, that is a shortened fingerprint. It's only 160 bits long. And you're supposed to recognize that, and you're supposed to reject it if it's not what you're looking for. Okay, I don't know who these guys are. I can't do that. And in fact, ADM did what's called the 2 billion SSH key attack, where you generate 2 billion proposed keys, and you just send the one that's visually the most similar. Does it trick people? Trivially. So, new field, I'm calling it cryptonamonics. The actual study of how you remember cryptographic variables. Anyone here still in college, by the way? Cool. Take some psych classes. Seriously, they're rather useful, even for the hacker types. So, what time is it right now? All right, 10:30. 3 classes of memory that are useful for cryptography. A, rejection. I've never seen that before. B, recognition. It's that one, not that one. I'm like, dude, recognition isn't that cool. What? Ah! Well, equal time. What would you do with $1 million? 2 screens at the same time. So, rejection, I've never seen that. Recognition, it's that and not that. And recollection. Here, let me just tell it to you. The way the human brain works, we have much larger capacity for rejecting stuff than we do for recognizing, picking out of a lineup, and we have even less ability to remember passwords for recollection. So if I can look at a password and be like, yeah, that's totally my password, and that one isn't, that one is, but if you actually ask me to come up with some sequence of letters, it's a lot harder. So you can actually take this down to our entropic representation abilities for certain signals. Whatever, let me just move on. We don't have time for me to figure out how to say simple things like sentences. There have been other attempts to make alternate representations of cryptographic entropy. Abstract art was used by a mechanism called deja vu, where they use computer-generated artwork. You can see that in the upper right corner. That has some good timing, by the way. Then there was another mechanism called passfaces that actually used dynamically generated faces. This attempted to move the problem of passwords from what people were typing in, recollection, which is very limited, and tried to move it to recognition. Pick the one of these that you recognize. Now the problem is that the amount of entropy that we can actually represent in pick the one that you recognize is surprisingly small, less than 2 to 16. Now this is okay, because passfaces is an online attack or online mechanism, and thus the user can be locked out, or an attacker can be locked out before their 59,000 tries are up. But SSH's requirement doesn't work like that. It's showing you a fingerprint, and offline you get to do whatever you want to try to break it. So we need something else. So what do we know? Oh yeah. Humans do not remember arbitrary strings of characters effectively. We know that failed. We do know that our brains can actually store a surprising amount of entropy. Homer's epics are enormous. We can certainly remember stories. But stories morph over time. They change, they go back and forth. It's actually a challenge for stories to stay stable. Our ability to reject a story that's changed a little is pretty low. But you know what's really stable in stories? Homer. Like the guy, Homer. Like the actual name. Names are an incredibly stable thing for the human mind to remember. They're the most stable entity in any kind of story. We seem to have some hardware or wetware acceleration for them. So what if we represent rejection proposals, instead of as a series of bytes, which we know is a failure, what if we represent it as a series of names? This is really weird, but I swear to God it works. So first, we take US Census data for names, which is available at the US Census. We note we have to have quite a few more female names than male names available. So what we do is we take 512 male names, 1,024 female names, and 8,192 last names. That's 9 bits, 10 bits, and 13 bits respectively. Now, we don't just take these names randomly. We attempt to determine we tend to get the most dissimilar names possible. We use what's called the edit distance, the amount of operations required to go from one name to the other. And what we try to do is we try to maximize the difference between every name that we pick. Because what we want is, if someone sees Bob and not Mary, we want them to see, wait, that's the wrong name. I don't recognize that. Or I'm going to reject that. That's what we're going for. I'm telling you details about edit distance because it becomes really useful later. But there are also some other acoustic measurements, like the old SoundX algorithm or Metaphone that the linguistics guys have come up with. But edit distance seems to work really well. Well, now we've got ways of representing 32 bits of information in chunks, and actually married couples. So yeah, you can take 160 bits and split it into 5 married couples, and it kind of looks like that. Instead of a big string of bytes, you get Julio and Epifania Dezudi, Luther and Rolanda Dornbos, Manuel and Twyla and Bessie. You have to show the names to your users every single time they log in, not just when something may have gone wrong, but it's shocking. It works. I spent like 6 months SSHing to every host that I went to with this. I could tell which one was the ones I knew and which ones wasn't. You just recognize the names. You might say, oh, but I'm bad with names. No, you're bad with names because people say their names really quickly, never say them again. If you're actually repeated, you actually start to remember names pretty well. Speaking of broken representations of entropy, OD-XTX1 foo. Nice little hex dump of a file. Wow, 6A-AC-06. This is about just as useless. Oh, but no, we've got a star. It's saying that this line has been repeated. Look at all those zeros, man. I really have lots of analysis of my arbitrary data here. There's got to be a better way to look at random strings of hex. And no, adding ASCII isn't enough. We need better ways to look at arbitrary data. For data analysis, first view of looking at new protocols. What can I say? I love me some new protocols. And of course, fuzzing. So, what's the deal with fuzzing? We got 2 main kinds of fuzzing out there, right? Dumb fuzzing. Take a file, flip some bits, see what happens. And we got smart fuzzing. Take a file, understand its internal structure, do all this analysis, fuzz in the structure, reconstruct back. Smart fuzzing is awesome. It does horrible, horrible things, but man, it's a pain in the ass to do. Dumb fuzzing misses a lot of stuff because it's just, well, dumb. We've got to find a midpoint. Well, there's this really interesting tool. And what it does is it finds structure. Instead of having to do it intelligently, it just looks at a random byte stream. And it's called Sequitur. Sequitur is a linear time pattern finder. It creates what are known as hierarchical context-free grammars from arbitrary input. And it doesn't slow down based on how much you give it. No, you can give it 100 megs of data. You can take the entire C Windows System32 directory, pipe it in, and it'll be like, oh, well, that's kind of cool. Let me create a structure out of this big amount of noise you're giving me. In short, Sequitur is 1000% awesome. But an example of what it's doing. Let's look at the switch statement at the left of this page. Someone bring me water, by the way? We're going to go from switch C, case 1, value equals 2, case 2, value equals 3, case 3, value equals 4. We're going to create a grammar out of that. And that is switch C, A1, B2, A2, B3, A3, B4, with A equaling, enter case, and B equaling value. This is interesting. We've just extracted meaningful symbols from arbitrary data. Now you might say, oh, but Dan, I can totally do that. I can see that myself. Yeah, you can see that in text. Try that in a random string of bytes. This did it with no user interaction. So let's do a trivia little thing, right? When you compress a file with Sequitur, each byte requires, because remember, A could lead to C, C could lead to Q. You have a tree that you have to traverse to recover each byte. You could actually color each byte by how far in the tree you had to go. I don't know how visible it is, but here are two examples of syntax highlighting of hex dumps just based on how deep in the tree you had to get. Now, obviously, when you have patterns, and the patterns have patterns, patterns and patterns have patterns, you end up going deep in trees for individual sections. And what do you see? Well, look at this. We've got this blob over here on the right. We've got these repeated sections. We have, we have structures that just pop out of the data. They just visually show up. Pretty pictures, useful, two great tastes that go together great. But can we do more? So I'm creating a tool. Context-free grammar's going to be a fuzzer. I'm calling it the CFG 9000. So the next thing that Craig Neville Manning talks about in his thesis, which by the way is also awesome. Yeah, it is a little funny. I didn't realize he was going to be the chief research scientist at Google, but oh well. So it goes ahead and it turns arbitrary data into the symbol set, right? Great. We can go ahead and draw graphs for how these symbols interact. And we see switch leads to case leads to 1, 2, 3, 4, 1, 2, 3, 4 leads to value. Clearly, if we do manipulations on these symbols, we will have much more meaningful manipulation than if we randomly swapped bytes around. I don't care how you randomly swap bytes around. Switch versus SITCH. Oh, I dropped the W. I've really done something meaningful. No, you haven't. Now, if you replace case and value, you might do something meaningful. System might not expect that token in that particular place. So, context-free grammar fuzzer, CFG 9000. Reduce the input data to a stream of symbols, fuzz on the stream of symbols. Shuffle the symbols, drop symbols, repeat symbols. Now, Sequitur is not necessarily the best way to generate this stream of symbols. In fact, there's an explicit line of separation between Sequitur, a symbol finder, and CFG 9000, which, given a context-free grammar, actually fuzzes that grammar. In fact, Sequitur might not even be the right tool set to use. There's a mechanism called suffix trees that the Protos guys are using. Protos, as you may or may not know, destroyed every single SNMP implementation in existence. They're good guys. I'm messing around. But Sequitur may scale better. I don't know of anything else that can find patterns in 100 megs of input without caring. Some sample output. Again, I don't have time to do live demos. I threw the source code of Sequitur into its own fuzzer. And what do we actually see? Calculate rule usage. P to rule P, to rule P, to rule P, to rule P. Calculate rule usage. Oh, open up calculate rule usage. This is all completely undriven. I just said, go take some symbols and go make some noise and show me some cool patterns. So everything that we can see because it happens to be text, we can also do because it's actually finding the boundaries between a function and what's inside the function. And that's pretty cool. So, things to do. I got to create Requitur, which is a version of Sequitur that's optimized for fuzzer use. I need to generate larger symbols. It's kind of built for compression, and compression doesn't care if it makes a symbol for a 2-byte sequence. However, that's not very useful because 2-byte sequences happen randomly in any data set of normal size. Kiefer Yang in 2001 created an optimization, which is basically if you have two symbols that are the same actual literal plaintext, merge them to one. You would think this would be obvious, but it affects some of the performance of Sequitur, so it wasn't in the original version. And you need to do this if you're going to fuzz all instances of a particular trope, a particular set of literals. There's an in-memory grammar requirement. If you are going to fuzz 100 megs of data, you need to have like 800 megs of RAM. There's a variant called Ray that does not have this trait and still keeps linear time. And of course, add the ability to import foreign grammars. I want to be able to interpret a series of files according to the grammar from another series of files. So I can say, hey, this looks like a JPEG. Well, how do I know that? Well, because it's got symbols from JPEGs. Cool. So Sequitur is really cool. It's unfortunately not where we need it. It's not necessarily where I even hoped it would be for BlackHat. But syntax highlighting for hex dumps, that worked. And we got some fuzzing out of it. Cool. Another approach. Dot plots. So I remember this old paper. I got a hobby. I like music, like actual music analysis. I remember this thing called visualizing music and audio using self-similarity. It's by a guy named Jonathan Foote over at Xerox. And this is a total brute force solution to analysis. You take a file, you turn it into little segments of time, and you compare each segment of time to each other segment of time. And if they sound the same, you make it white, and if they sound different, you make it black. And there's a tool out there called disassociated audio that'll do this if you're also into audio. Well, what kind of pictures do we get? We get pretty cool pictures. You actually have each individual section. This is Day Tripper from the Beatles. And you actually get each individual section from the bridge to the verses. That's where all these little color sections are. They look substantially different. Can we get this out of targets of data that we might fuzz? Anyone actually see Pirate Baby Kanbana Fight 2006? Yeah. Awesome. Pirate Baby MPEG says yes. We can absolutely find fuzzable patterns in a huge number of data sets. Hey, if we can do this to audio, we sure as hell can do this with some set of bits on a hard drive that got compiled by some tool. So what exactly are we doing? Well, Jonathan Hellman's dot plot patterns, a literal look at pattern languages, offers an introduction. So take to be or not to be. Down the center, to is to, be is be, or is or, not is not, etc. So no matter what, we're getting a diagonal line, right? But look, that to be in the upper right corner, to be gets repeated between the beginning and the end. So we get these extra dots along the side. That shows a repeat, right? Now we need to do this instead. If we're going to do this to files, I don't want to use individual bits, although Hellman actually does in his paper. I want to use sections, and I need to figure out if the sections are similar. Remember how I had this similarity metric sitting around from when I found the difference between all the names? We can totally use that to find similarity between, say, 32-byte chunks of a file, and it'll work great. So what do we see for various data sets? Oh, actually, I got to do a little bit of history. The bioinformatics guys, who are the only people who deal with legacy code issues uglier than ours, they go ahead and they use this stuff. But no one, as far as I can tell, has used it to guide security research. Well, what would we want? First of all, we'd want to get a global view of section boundaries. Can I separate out clearly different sections? Secondly, I want a local view of what exactly is going on. Given a certain pattern, can I make some degree of conclusion over visually what's showing up? Java class files, .NET assemblies, CNN's homepage. Oh, we've gone to HTML, which has redundancy on a much tighter scale. And interestingly enough, we see that in the data set. Is that at all visible? I hope it is. SMB torture traffic. We can throw packets into this. Packets being much smaller units of data, packets have their redundancy and differences at much higher frequency. Kernel32.dll. Now, the one thing to notice is that we're actually able to uniquely identify individual sections in this file. We've got this block here, this block here, this block here. Here's one, here's a couple of small ones. Here's a large block that has internal small blocks. The idea behind this process on the global scale really works well. Like, for example, human chromosomes, in case you feel like hacking other viruses. The Legend of Zelda. Does anyone here actually know 6502 code? No. But can you identify individual unique sections a hell of a lot better than you can with OD-X? Yes, absolutely you can. Unique section, unique section, unique section. Everything here that creates a grid pattern, and no, the shirt wasn't accidental. Everything here that makes the grid pattern goes ahead and represents another deviation in the file. So I'm releasing a tool shortly. It does autocorrelation, so I'm calling it hardcore, that calculates these images. It's pretty cool. It's really fast because I ported it to C. Nothing says 80 times speed improvement like porting to C. You end up hacking IMAX style because you end up with all these images that are like 10,000 by 10,000 pixels. It's kind of cool to know, man, I need a better view of this. I'm going down to the IMAX theater. The global goal is totally achieved. Fuzzing is a combinatorial game. If you can split the combinations from multiplicative to additive and split out each section individually, you are ahead of the game. You can say, I'm going to do this block, this block, this block, and even if you dumb fuzz that block, and that block, you've at least separated out the problem. Cool. Well, can we get any local knowledge? Is it at all meaningful what particular visual patterns show up? Well, from the original paper written on the topic, we actually can get some documentation of what's going on. So, for example, if you have a series of A's and then a series of B's, you will get 2 squares along a diagonal. If you get a repeat, ABCD, ABCD, you will get just straight diagonal lines, just like we had with 2B or not 2B. If you get 2 blocks that look like they've kind of interacted and there's kind of some shuffling going, you get both diagonals and squares, then you have 2 types of data that have been shuffled in. Now, because we're looking at blocks that have potentially multiple things, you might have 2 different sub-message types inside of your analysis window. You'll get light crosses, broken diagonals. I encourage you to actually get that paper. It explains a heck of a lot of what you're looking at. But it also doesn't, because there's some weird stuff inside of symbols. It's the mark of a good tool if it shows you weirder things than you can possibly imagine it would have originally given you. You get these lines that have fade outs. You get blocks that look like artwork. You get very highly detailed stuff. And then over here, we get like squares, like fairly large size squares. What's going on? I don't have a freaking clue. I don't have any idea what's going on there. What the hell? And that is awesome. Because I sure as heck didn't know that anything was going on when I did OD-X, but I didn't even know I didn't know what was going on. I just figured it was like random noise. This gives me clear separation. If it's random noise, you get a big gray blob. Now, what's actually kind of interesting is if you have random noise with a little bit of a bias, a little bit of sections, you'll get gray with slightly less gray. Now, whether a computer can see it is another question. Whether your occipital lobe can see it, oh yeah. Yeah, I got me a third of my brain dedicated to vision, and believe you me, I'm willing to use it. So, what do we got to do here? We got to figure out what the heck all these things visually mean. We've got to create some interactive tools for dot plot evaluation. Hey, we can call the field data microscopy. Color. Got a lot of our brains dedicated to color. If we just use 3 different similarity metrics, theoretically, we should get 3 different views on what's going on. Things that don't work, viewing across different window sizes, for whatever reason, there's self-similarity, you just get blur. It's not very meaningful. I did come up with a construction for turning arbitrary compression algorithms into a similarity metric. You can do it. The problem is they're too good. They find similarities in things that you can't actually see. Now, this may or may not be a good thing for your uses. It visually is useless, though. It destroys the ability to do segmentation. Now, figuring out exactly what it's finding, that's an interesting question, but it's a different project. Better symbol selection. You want to find similarity. Right now I'm doing dumb comparison between bytes. Becoming x86 aware, doing jump target normalization, integrating context-free grammars from Sequitur, re-implementing pretty much everything Halvar's done and moving into the visual realm. Awesome. We can do all that kind of stuff. Now that's things I might do. We got a couple minutes left, 8 minutes. You don't think I'm done now, do you? Now, autocorrelation is interesting. Cross-correlations were the real fun results. In autocorrelation, we're going to compare A to A. In cross-correlation, we're going to compare A to B. Now, I hate to admit this, when you take 2 different files and compare them using this method, it looks like crap. Almost always. Not always, but almost always. There's a really notable exception. And that's if you take 2 versions of the same binary. All right, I've managed to skip enough demos. I've got to show at least one thing live because it's pretty cool. We are going to take 2 versions of a particular DLL. Actually, come on. Yeah, this is what happens when your images are 10,000 by 10,000. They take a little while to load. Actually, I think this one's even bigger. All right, check it out, right? I think I can make this full screen. Maybe. Yes, cool. No, that's not cool. Hang on. So it's actually going to try to zoom in. I don't want it to zoom in. Or zoom out more accurately. So we're looking at a 16K by 13K image, right? And this is 2 DLLs, 2 separate versions, separated by about 2 years of development. And let's see if we can find similarities between them. Well, here's just the beginning of the file. Not that much similar. We've got a diagonal here. We've got a diagonal here. But let's just follow the broken line. Oh, broken line. Code inserted, back to normal, back to normal. Oh, look at this, another break. I don't know if you could automate the line finding, but you can certainly see it. All you're doing is I don't know if it shows up on screen, but there's actually a line. It's a broken line that traverses down here, and you can follow it. And this is basically a binary diff between two versions of the same DLL. So, cool. And of course, I've got slides, this in the slides as well. Here's a shift, an insertion. There's deletions if you get vertical slope increases. MSVCR 7.0 versus MSVCR 7.1. Here's just straight up new code shows up in 7.1 because you get a nice vertical line right here. Oh, I didn't expect this would actually be as useful as it turned out. So, I can't believe it. I'm actually going to be ending on time with time for questions. In summary for the day, your VPN is under threat. If you actually want the ability to not go into work and not commute, you should probably tell the bosses the telcos are out to mess with you. I can develop the test, but if steroids aren't illegal, a test isn't useful. Check your devices for generic SSL certs. I'm going to be working with some vendors. That's one of the reasons I'm not naming names. The guys in the room who know what I'm talking about, don't do that. That's going to be really embarrassing when that comes out. Fix any application that submits to HTTPS from HTTP. It's not difficult. You have straight up JavaScript. It's great. It's trivial. If you're using DNS, I told you how to fix that. Stop expecting users to remember long strings of hex characters. There's cover your ass, and then there's come on, you're full of it. Fuzz your file formats. Dear God. Way too few software vendors are doing that. And take a look at your data. You might be surprised at what you find. That's what I got. We got any questions? Where? Go ahead. Hang on, why don't you actually come up? Because I don't think anyone else is going to be able to hear you. Because I certainly won't. Just come up to me. Oh, you're getting, okay. Mic duty's coming. Cool. All right.
Hello. Oh, it's on? Okay. So you have those pretty graphs, and you can see the various patterns, but then can you translate that back to what program addresses the different areas correspond to, so you could actually use that information?
Yeah. So the game is that you can have really inefficient algorithms that if you tie them to just look at this really tiny window, they'll be incredibly accurate for. So what you do is you'd manually trace out, or you'd attempt to automatically discover the similarity line, and then use much more accurate algorithms after that to go ahead and go from the line. Because I mean, when all we're talking about, the XY coordinates, are chunks of the file. So you can go from a visual coordinate to byte 100,000 here is very similar to byte 834 there. You can just straight up do that. So it works really well. Nope. It's a linear correspondence between location in the file and offset in the graph. That is I totally see where you're coming from. It is maintained.
I owe it thanks for a living.
Hang on, someone with the mic go.
I owe it thanks for a living.
Good. Can you tell them to stop screwing this up? It's really embarrassing.
I'll start with the more basic. I'm working on more basic issues, actually.
Okay.
Like, you really shouldn't store social security numbers in plain text in your database.
Yeah.
Yeah, we're at that level with, or with some people. You should encrypt your databases sometimes, and I get pushback on that. So that now, now.
So the one
not uniform. Some banks are way up good.
The one difference that I'll say is that there is some fundamental difference between problems at the back end that no one can see and problems at the front end that are really stupid looking. Especially when the why is this secure is like You can say it's secure all you want, but you know who else can say? The phishers that are costing you a crap ton of money.
Oh no, absolutely. And in some places the message is well received, and in some places you point out people are violating their very own published secure privacy policies, and they don't want to spend money to fix it.
Yeah, it makes sense. I mean, hopefully with the existence of a very cheap and very straightforward solution that maintains what the user interface guys absolutely want, we'll see some traction. They're banks on the top 10.
I know.
All right, go ahead.
What do you think of audio for real-time differential analysis as opposed to using video? Put a set of headphones on and just listen while you work.
Oh yeah, that's one of the things that I tried doing, right? So it turns out if you take a data set, you compress individual blocks. What you get is you get a signal, a 1D signal, that looks like it would be interesting to make audio out of. So I use this code base called Pratt, and I actually tried it. And it didn't sound very good. It may be possible, especially if I can get a backwards transform between the vision and the audio. But if you just look at the amount of raw bandwidth available for data analysis, we have a lot more visually than auditorial. Audio is really good for sustained signal stuff. So just like stuff in the background, be like, wait, I've never heard that before. Audio rules for that. Well, hang on. Let's. I don't mean to skip, but I've got a couple people asking. But find me later. Here.
Oh, you got another question?
Yeah.
Yeah, I just want to say hi.
Oh, hey, Dennis.
Okay.
Rock on. What's up? Okay.
Anybody else got another question?
Are you going to publish all the SSL certificates that you collected, or for, the top 50 of them by frequency, maybe?
Oh yeah, I forgot to mention this. I should have mentioned it during my talk. If you want to see what your company is exposing, send me an email. I'll have someone from IOActive send it back to you. I'm not going to show what everyone's doing. I may do top 50. Well, except for the one that I shouldn't. Like I said, they know who they are. Oh yeah, here we are.
Yeah, on the iframe stuff, if it's in an iframe, then the user can't see the padlock.
Oh no. This is the okay. Actually, no, you can keep that. Actually.
Yeah, I'm trying to keep it.
Oh yeah. So the deal is that the user doesn't know the iframe is opening up.
Right.
But when they go to the password thing, it flashes over, and when it flashes over, then it's secure. And what you do then is you have a padlock be open, and you have the padlock close. So you actually, on the SSL site, as opposed to the normal site has the padlock open. When they go to type in the password, there's a weird flash, and then the padlock moves. This shouldn't matter. It totally matters.
Wait, I'm sorry, I'm not quite following. I'm
Okay,
talking about the padlock on the bottom right that should appear if you only have one iframe that's HTTPS and the rest of your page is HTTPS.
The idea is that you're just using the iframe to preload the contents. So when you switch over to the SSL site, just because you went to the, you added focus to the password window, when you move over, then it pops you. It does a page redirect. It does window location href.
So what was the point of the preload then?
You're just using, no. The preload is to make the switch over fast.
Oh, so it's just an optimization?
Yes.
It's not a security benefit that you're talking about?
Well, it's a security benefit because people actually start doing it. What is it that they want to refute? It's perf, right? Yeah. Perf we could solve this problem by having, like Wells Fargo does, because I can name names when they're doing good. Wells Fargo has every single site you see on their page come in over SSL. Unfortunately, this is very expensive and a pain in the ass to maintain. But they do that.
I thought the overhead for SSL wasn't all that bad.
The overhead for the actual bulk data is not that bad. The overhead for session initialization is a pain in the ass. Enough that you do not want to do it for every random person who's browsing your website. You really only want to do it when they're doing online banking.
Okay.
I mean, that's just what the data seems to say.
Okay. Thanks.
Anybody else got any other questions?
Go ahead.
Yeah, I had a question on the iframes. Is it browser dependent? Does it work on all the browsers? Will it look the same way in all the different browsers?
Works great everywhere. Standard behavior.
Okay, and then the other one I had was on SSL. Does it matter if they use form-based posting on the website or digest?
Well, pretty much everyone uses people have abandoned basic auth and digest auth and all those kind of things for scalability issues. Will it work? Yeah, no. Yeah, that would work great. Well, let me think about that.
Right, because what I've seen is if you're using a man-in-the-middle attack against an SSL site, it tends to, if they didn't do it right, they tend to do basic form-based posting, and then you basically grab all the information, just converts from HTTP to HTTP.
Yeah, well, so the idea is that the idea is a user should not provide their personally identifiable information, especially if it leads to their money, unless they have reason to believe that the thing that is requesting it is secure. The banks have turned this into, well, as long as it actually eventually goes over a secure line. It only goes into a secure line if there's no bad guy. If there's a bad guy, you're screwed. But I thought the whole point is that we're trying to defend against bad guys. So yes, if the idea is that the initial form comes in securely, but the moment you try to do anything with it, it swaps you over. And the idea is that the user should be trained, don't type in your password. You can type in your username, but don't type in your password until you see the lock. And if you don't see the lock, don't put it in.
That seems like a hard thing to train, because what you're really doing is, it's normal to have if it was a bad guy's altered page, then it just wouldn't switch and the user would keep typing in their password.
Yeah, well, the thing is, the switch is actually somewhat visually intrusive. You would notice if it was missing. You'd be like, that's funny. It didn't flicker for a moment. Something's wrong.
Hopefully.
Okay, yes, I am being hopeful, but you know.
Have you seen the paper on how phishing works?
I've seen a couple. Which ones?
Yeah, I can't remember the guy's name, but it's about what the users will check for. And the visual graphics is something that, if the bad guy emulated the visual graphics, they'd probably be more likely to actually put the details in.
Well, look at the state of affairs. You know, 26% of major banks are building stuff that is defined as trivial to phish. And they're saying, why this is secure. And they're putting pictures of padlocks, ugly padlocks. It's, you know, if it could be a very clear message to users, you do not put in your creds unless you see security, you know, that'd be a clear message. As opposed to what you have now, which is banks you ostensibly trust being creative with the standards they're trying to deploy. Now, how's that?
Hey, pleasure listening. I was thinking they need song titles or haikus for those SSH fingerprints. What do you think?
Do we have sufficient... Well, we have collisions on song titles.
Yeah, love, you know, just the word love, God.
How many songs do you think have come out over the past 100 years that have any degree of popularity? Let's say we got 16 bits per. You might be able to represent 64 bits of entropy using 4 songs from the last 100 years.
Well, then you throw in like city names or something too, so you like...
You have a limited capacity. I mean, I've tried things like that. I tried actually using city names. It didn't work that well.
Awesome.
IKEA sec, given that...
Come on, you fixing that out now?
Fixing Finnish security with Swedish furniture. Is there any other kind?
Hey, that's my partner.
That's interesting, because if it was like city names or song titles, there's associations with it, so it might be easier to remember than just kind of random names of people.
My suspicion is that we'll probably be able to do 2 couples reliably. Like, someone needs to actually do the study of how many names you can reject. 5 couples is probably a bit much, but I mean, even if we can get 64 bits of strongly rejectable data, that's so much. What do we have now? A couple bytes, a couple characters? We have crap now. But so cities were something I thought of. They didn't seem to, because I mean, self-experimented. I worked on this stuff for, tried various variations. There's also not as much variation in city names as you would think. I was trying to have Bob and Kelly Kapipsi from Idaho, or Fu, Idaho. It didn't work that well. Oh, and it's also even more than the names are. You know, we here know all 50 states. Outside of the U.S., it's much harder. Whereas the names are actually distributed by just what sounds different. So you actually get names from around quite a bit of area.
I have a question. You showed how to visually see differences between 2 files, like maybe a variant on a file or a redo on a file. do you think there's a potential for fingerprinting, if you will, who came up with a variant on a file? Like say you got a piece of malware and the next variant comes out, and you diff those files, and something that you might be able to tell based on what kind of differences these people put in to obfuscate the code, and for just to make up the next variant, that it might be worthwhile to look at that to identify which malware variants come from what particular person, so that later on when you identify them.
Small data sets tend not to work that well. However, at that point, because you have so little data, you just look for what's called the longest common string and see if there are common strings that did not come from just how compilers work. You know, what you're looking for is, show me a signal that comes from malware executable code, but does not come in from, you know, Microsoft Windows, or, you know, out of GCC normally.
Gotcha.
And that may, you know, frankly, I'll try it. It's an interesting idea.
Thanks very much,
Okay,
Dan.
we gotta
Good
go.
stuff.